in CSC department, KL University, Vijayawada. He has received his MSc and MPhil in physics. Also, he has done ME and PhD in computer science and engineering from Satyabhama University, Chennai, India. He has more than 15 years experience in academia, research, teaching, and academic administration. He is senior IEEE member. Also has published more than 50 research papers with 4 patents. He's a reviewer and editorial member in various IEEE journals. It is really a pleasure for all of us, Professor, that you have joined us for today. And the topic which we have picked up, the quantum computing, is actually one of the very recent topic which is coming up with the recent world. And we hope our students who are there in labs and classrooms, and also the persons who are going to see you on Facebook Live will be benefited from your presentation. Over to you now, please.
Thank you. Namaste. Okay. Okay. Thank you, Professor Sandeep Kautish, for giving this opportunity. Okay, students. And faculty members, let us start our topic. So our topic for today is quantum machine learning. So initially, I will start with some introduction regarding quantum computing. Okay, and then I will go for showing you some important coding in quantum machine learning. I will explain you some quantum machine learning as well. So main topic for us today is quantum machine learning using Qubits. Qubits is a tool that is developed by IBM, because IBM are the front runners for developing this tool, which is very useful for doing a lot of quantum computing applications. Also, quantum machine learning is the latest one which Qubits has developed. In fact, the coding that I will show you, it was actually developed in 2017 itself. But people are not aware of quantum computing. They are not using this because many other things they are concentrating. They were concentrating on regular machine learning and regular deep learning. So they did not concentrate much on why? Because they thought that quantum computing requires true quantum setup for installing and for purchasing that infrastructure and working on that. But they don't know, they are not aware that IBM provides a Qubits tool on which you can really work standard preliminary quantum computing as well. Okay, even it gives for 1 month free trial for the students also to work on this particular important quantum machine learning applications. Okay, so I will start with some introduction. Why quantum computing is required, okay, and how it evolved. So in the early stage of before 2010, there was nothing like quantum computing. Nobody discussed we know what is quantum mechanics earlier. We know what is classical mechanics if you are a physics student. So classical mechanics are the things which we can see with our naked eyes. Okay, quantum mechanics deals with the particles which we cannot see by naked eye. We need to see with the microscope. Okay, so by 2020, as we are in 2022, but this information which we collected a few years back, okay, they expected that transistors will be so small and it will go to a micro nano scale, and it will be generated so much heat that it will standard silicon technology will be collapsed. Okay, why? You can see everybody watching latest technologies online, YouTube, in movies, many things you are seeing. Silicon chips are going to the micro level possible. Okay, so so many things are becoming at a nano micro scale. What is an example I can give you? We used to use floppy disk in the 1990s and 2000, early 2000. Okay, later on pen drives came, you know very well, and CDs, hard disk were there. Okay, so now you can see that a small USB also, we are having 120 GB USBs also are available, and small small chips which are hardly 3 centimeters length chips also are available, which will carry a lot of information. So Intel is growing rapidly day to day. Okay, with a 32 nanometer silicon technology, it is already implemented. So the scalability is so huge, you can say, right? So electrons tunnel through micro thin barriers between wires corrupting signals. Okay, so what exactly these quantum computers can learn? That is the one big worry. See, if quantum computing will become realistic, as already IBM has introduced, Microsoft has introduced, even AWS has introduced quantum
Officer,
computing
sorry to
learning.
interrupt you. Your
Yes,
slide is
sir.
not visible.
Why? It is not shared.
Yeah, I think.
Okay. Now,
Yeah. Please press F5.
I think somebody stopped sharing maybe earlier. Now, can you see?
Yes. Please go ahead.
Okay, guys. Yeah. So what exactly quantum computers can learn? Okay. What is the help of these quantum computers is you will be having a lab filled with 200 computers in the lab, ordinary lab. Okay, where you have your Dell or HP desktop computers. Okay, the maximum capacity of that can be 1 TB. That's all. More beyond that 1 TB projects beyond to work, it finds difficult for you to work on those. But all those limitations can be overcome with the success of quantum computing. So quantum computing will increase the scalability for you for implementing learning. Okay, and it will also help you for recognizing different objects. So writing an energy program for this task would be very difficult. Okay, like if you are using a quantum compiler, so as we know that how to capture the essence of objects that system must recognize is the thing which you have to take into consideration. But luckily, there is a way around, okay, in which quantum computing we can tweak this energy program in response to new pieces of incoming data. So you can slice the data and you can partition the data and you can give the data pieces, and this energy program can be successful. So it also allows machine to make a good success at what an object might be, and it can also see that a particular instance of it before. Okay, so this is a simple definition you can say of what exactly quantum computing consists of. Like sometimes we may expect like to define quantum computing mathematically. Okay, so it is nothing but quantum computing is a collection of n qubit register or a set of registers. It's an algorithm in a form of unitary matrix. So that is nothing but the software that what you call it as. Okay, and also it measures to extract information we need. Okay, that is the display, right? So more formally, we generally explain quantum computing with the help of Hilbert space. So a quantum computing is the set consists of h comma u comma m, where h is the Hilbert space. Okay, is a n qubit register. Okay, and u algorithm represents what? A quantum algorithm, and m is nothing but what? The third one, the measurements to extract information. Okay, so three things are important for a quantum computing definition. First one is the Hilbert space. Second one is the quantum algorithm. The third one is the set of measurement operators. Okay, so generally, if anyone asks you to define a quantum computer or quantum computing, what is quantum computing? So you should be able to define in this particular form. Okay, right? So I'll give one important slide where from University of Cambridge, they explained what exactly is quantum computing and what all the things that are mentioned in quantum computing. As you can see, from the Charles Babbage engine that was developed way back, okay, so from there to silicon wafers, and to deal with atoms, okay, to deal with atoms, we need to perform using quantum computers. Okay, so this diagram will show you like every 18 months, microprocessors actually double in speed. Okay, and what are those qubits we will see, right? So the classical bits which we deal are nothing but 0 or 1, but the quantum bits we can deal with a 0 or 1, combination of 0 and 1 also. So you no more will be discussing like bits, bytes in general traditional computing language. We will be discussing in qubits here. Okay, so you can see a classical register. If you can see it's 101, like here you can see, this is a quantum register. Quantum register consists of this total 8 information. Okay, so 8 bits of 8 bytes of information, sorry. Okay, and once this register is prepared, quantum register is prepared, this register is fed to a quantum processor, f of x. Okay, the superposition of different numbers can perform operations on all of them. Okay, so that f of x, it will represent with this particular f of 000, that is each byte of information is taken, and this represents clearly. Okay, and you can see how we exactly build quantum computers. We actually follow some logic gates, okay, technology, and we form this quantum computing. You can see here, input we are having here, and you have these quantum logic gates, and we have the output here. Okay, right? So how to build quantum computers and what are the promising technologies, who are the important stakeholders are there, or who are the important companies they are evolving this technology, these things will be seen. Okay, so the difference between bit and qubit is like, in bit, 0 is the smallest unit of information present computers, and it represents only one or two values, 0 or 1. Whereas a quantum computing, if you see, we deal with qubits, where quantum analog of the classical bit, it can take on two values simultaneously. It can take 0 and 1 simultaneously. So this characteristic expands possibility of producing parallel calculations. Yes, please. Any problem? Please mute yourself. Okay. So this characteristic now expands possibility of producing parallel calculations. Okay. This is simple architecture diagram which is important in quantum computing, where we have, see here, the physical layer attributes you'll be having, and the classical computing technology is fed to the quantum computing technology. And after combination of all these, okay, the data is given to the quantum computers, and from quantum computers we generate quantum algorithms. What are the other things that you will be taking into consideration are quantum information processing, quantum error correlation, fault-tolerant quantum computations, measurement and controlling, quantum registers, gates, circuits, and memories. Okay, so this is a very important architecture diagram, a brief architecture diagram, I can say, which will give you what are the things required, okay, internally for a quantum computer. Okay, then the milestones, if you see, what are the milestones of quantum computing? We have three important things are there. One is quantum annealing. Second thing is gate-based quantum computing. And the third one is commercially, how can you use this quantum computer? Okay, you can see here, quantum annealer, generally what it does is it demonstrates practical utility, and quantum annealer demonstrates quantum supremacy. Also, experimental quantum annealer is available. Okay, and the smallest possible of qubits, gate-based quantum computer you have here at the ground level, and we can increase the scalability to 50 plus qubits while maintaining gate fidelity. So gate-based quantum computer demonstrating quantum supremacy, you can see here. This is again given into three different things here. One is gate-based quantum computer. Here we are increasing the scalability from 10 to 100. 10 to 50 we have done here. 50 to 100 qubits we are doing here. And also the gate-based quantum computer is demonstrating practical utility, and gate-based quantum computer demonstrating QEC. Okay, right. So then we have here, from here you can see here, gate-based QC with running hundreds of qubits running simultaneously, and high fidelity logical qubits will be using. And also there is a possibility, if you increase beyond 100, 1000 logical qubits also can be worked on a single model. This is due to the large fault-tolerant modular quantum computing. Okay, so this is one other important architecture diagram or a framework, you can say, where you can see old version of CPUs and GPUs you have seen in the left-hand side, and we are going to see quantum processing units in the future. These are things which we will consider for computing resources. Okay, so Ocean Software is one which has given this simple diagram for a framework for quantum computing, where It includes graph mapping, constraint compilation, simulated annealing, D-Wave API. D-Wave is a powerful, industry which actually builds up quantum computing real time. Okay, it also produces latest computing technologies, latest equipment, latest hardware. It is an US-based company, very large-scale company, and this is the first company which actually uh, bring into picture, or you can say like realistic into picture, developing a quantum computer. Okay, right. So hybrid sampler. Okay, and we are also the problem suitable for QPU, quantum processing unit. Also, we will consider two things while we are considering quantum computing. Why? Because we want the maximum scalability, and it should be executed in a minimum short of span. Just a second. Hello, hello. Amma, 3:15 or just 3:15 login. Okay, sorry for that. Okay, so we have also optimization and constraint satisfaction problems, two things. Why? Because when we are discussing more scalability, quantum computing, when we are discussing more about scalability, large things you want to execute simultaneously and within a less span of time that you are planning to execute. So optimizing the task also is important for us, and also to avoid constraint satisfaction problem. Okay, that's why we'll be taking care of like social network analysis, web methodizing, traffic flow, okay, portfolio optimization, scheduling, circuit fault detection. Okay, right. So this is one of the important quantum world association. They are given one particular, how each of these software companies, MNCs, top level MNCs, how they are dealing with quantum computing. Like how IBM and how Microsoft, how Google, they are dealing with quantum computing. So we have now in IBM we have the full stack libraries they use with the script. Okay, in Google they use CARQ, and in Microsoft they use quantum development kit. Okay, so there are various quantum algorithms are there, various quantum circuits are there. Okay, we have the assembly level languages also are there. Like in IBM we have Open QASM, where in Rigetti we have QUIL, in D-Wave we have QMASM. Okay, in Google we have machine instruction languages. Okay, so CARQ is a powerful library that Google is using. Okay, QAsh is the one which Microsoft uses. Okay, so these are some of the quantum universal languages that we are seeing in reality at present. Okay, we have a lot of what you can say library files that we can directly include and we start working. Okay, just imagine only IBM was there in the beginning, then Microsoft, Google have developed, and now even Amazon, AWS also have given some particular libraries for using quantum computing. Okay, so as a student, you will be interested in like what are the companies that offer placements. Okay, what are the things that are providing consultancy services or new funding strategies. You can see here. Okay, you have here IBM, Microsoft, you have D-Wave, Rigetti, Nokia, Bell Labs. Okay, Oxford Quantum Circuits, Kilimanjaro, IonQ. These all things, Alibaba Group. These all things are giving placements for students who are certified in quantum computing global certifications. Okay, we also have quantum consultants. You can see H5. Okay, you have 1Qbit, you have entanglement, you have TOS, Zapata computing. We have Netramark, we have QC, where Kilimanjaro. Okay, many things are there, as well as there are some funding strategies also there, like Qubit protocol, Quantum X, Creative Destruction, Quantum Revolution Fund, and Quantum Valley Investments. Okay, so this is the what is D-Wave company that I told you, which is the one which brought the first commercial quantum computing system into market. Just type D-Wave company USA, you will get complete details of D-Wave company. Okay, right? So then we have important terminologies that we generally see. What are the things we see when we start studying quantum computing? So quantum insert, quantum bot, quantum biscuit, quantum DNS, quantum hand, quantum phantom, quantum sky, quantum copper, and quantum smackdown. These are the things which they started from the year 2005 till 2010. These are things which came into being and they became operational. Okay, so quantum bot got operational in 2007 itself, and it was highly successful. More than 140,000 bots were implemented in 2007. Okay, so these are very important terminologies that we should be aware of. Okay, right? So these are the things which will be generally coming across when we are learning quantum computing. Bits, Pbits, Qubits. Pbit is the probabilistic bit, and the configurations we will see 0 and 1 bits. Okay, but you won't be executing simultaneously in traditional computers, but in quantum bits you will be implementing them simultaneously. The description also you can see here, alpha and beta will be seeing in quantum bit, and the observation you can see alpha mod alpha square percent and mod beta square percent will be seeing. Generally, the evolution you can see from determinist stage to stochastic stage to unitary stage we have seen. Okay, from bits, Pbits to Qubits. Okay, and the three known types of quantum computing and their applications. Okay, mainly are the computational power is a very important aspect. We have quantum annealer, you have analog quantum, and also you have universal quantum. So a very specialized form of quantum computing with unproved advantages over other specialized forms of conventional computing. We generally call that one as quantum annealer. It is at least powerful one, you can say, and most restrictive form of quantum computers. It is the easiest to build. It can only perform only specific function. The consensus of the scientific community is that the quantum annealer has no known advantages over conventional computing. So the applications you can say optimization problems and general. If you bring into generality, you have restrictive and computational power, same as traditional computers. Okay, traditional computers. Okay, right. So the second one is analog computer, analog quantum computer, where the most likely form of quantum computing that will first show true quantum speed up over conventional computing. This could happen within the next 5 years, as they said. Okay, right. So now we are dealing with this analog computer. In reality, in 2022, we are also implementing hands-on this analog quantum computing. The applications can be like quantum chemistry, material science, optimization problems, sampling, quantum dynamics. Okay, so generality is partial and computational power is very high. So the analog quantum computer will be able to simulate complex quantum interactions that are intractable for any known conventional machine or combinations of these machines. It is also important that quantum computer will contain between 50 to 100 qubits. Okay, the third one is very high, you can say, the scalable universal quantum computer, where the true grand challenge in quantum computing, it offers the potential to be exponentially faster than traditional computers for a number of important applications for science and business. Okay, what are the important applications that we'll be seeing in universal quantum computing is secure computing, machine learning, cryptography, quantum chemistry, material science, optimization problems, sampling, quantum dynamics, and searching. And the computational power is very high, and generality, if you see, complete with known speed. Okay, so it is the most powerful that we expect and most general and hardest to build. Okay, but number of difficult technical challenges we come across, then only we can implement 1 lakh physical qubits on this universal quantum computer. Okay, so these are the common applications that we see in quantum computing. That is cybersecurity, drug development, financial modeling, better batteries, cleaner fertilization, traffic optimization, weather forecasting and climate change, solar capture, electronic materials discovery. Okay, so also we have seen these are the 4 important fields of application that people are doing research in this: cryptography, medicine and materials, machine learning, and big data analytics. Okay, so because see, cybersecurity is the main problem for us, and cyber defense is a very important, challenging problem for military armed forces as well. So providing the best possible no secured information is important. So for avoiding snoopers and hackers, quantum computing will be very helpful, because hacking a quantum computer is impossible. Okay, that's why quantum cryptography is developing in the present day scenario. Okay, so medicines and materials, if you see, quantum computer also is useful for providing simulations and understanding a lot of natural things, like how micro level things like molecules, atoms, how their interactions are forming, intermolecular interactions or intramolecular interactions, how they are studied. These things are really possible using quantum computer. Also, if we go a little bit more deeper into machine learning, the research indicates that quantum computing significantly accelerates machine learning and data analysis tasks. Okay, if you see the big data analytics, where quantum computing can search ever-growing amount of data being created and locate connections within it. So it is very much faster than classical computers, the classical big data analytics that you are seeing now. Okay, there are some limitations are there. So quantum computers are very difficult for an ordinary engineer for building and developing some programs. As a result, they are crippled by errors in form of noise, faults, and loss of quantum coherence. But after a little bit of in-depth study, we can really fix those errors and bring it to reality. In quantum computers, such errors arise from non-ideal circuit elements and interaction of qubits with environment around them. So for these reasons, the qubits can lose coherence in a fraction of a second, and therefore computation must be completed in even less time. Contrary to myth, quantum computers are not known to be able to solve efficiently the very hard class called NP-complete problems. Okay, right? So these are things which you generally study in optimization. Okay, so there are several other limitations on a quantum computer. Although qubits can hold many possible values, only one classical result can be obtained from every run. Therefore, output is probabilistic. So repeated runs may be necessary to obtain the desired result. Computation must be reversible, and it is impossible to copy qubits. There is no cloning theorem available. This is one of the important, like how quantum information is evolved from 2010 to present day, and how the future will be till 2040. Okay, this was given by Japan Society of Applied Physics. Okay, as you can see, 4 important things are there here: computing gate and processor, communications cryptography and network, quantum new technologies, device and fundamental technology. You can see the practical quantum computers. If you see, the quantum gate operation is performed, and quantum computer testing beds and algorithms are used here. Prototype of quantum computer for all-purpose large-scale architecture is executed here and implemented using quantum simulators. Okay, and the universal quantum information network provides for quantum crypto network and quantum secure network. Next, if you see the quantum new technology support in daily life, like how we can see the basic technologies of quantum metrology, okay, and different applications of quantum metrology and different applications of ultra precise frequency standards can be seen. Also, we'll be using quantum lithography, okay, and when we consider high performance quantum information devices, single photon generation, single photon detection, and fundamental technology for qubits and Q gates we'll be using. Okay, and multi-qubit technology you can see. There's also provision for quantum media conversion and large-scale quantum memory. This is the roadmap that you can see. Okay, from HPCs to quantum computing, from 2015 to 2025 and 2040, how things evolve. What are the basic things that you consider in physical modeling? What algorithms we will see? What is the geometry and grid generation? How the knowledge extraction is done? Okay, so how we define standards for coupling to other disciplines, you can see. Okay, so now we'll be seeing a little bit of very important quantum machine learning, how things are discussed, how we actually install quantum computing, quantum machine learning. Okay, you can see here. Okay, so this is a popular website, okay, which everyone, I will share you the link in chat box. Okay, so Qiskit, this is the one which I was telling you, in IBM we'll be using IBM Qiskit for executing and implementing quantum computing. Okay, right. So you can see these are some of the tutorials are available online. Okay, so we can study Qiskit machine learning. Okay, so first initially you need to install. How we can install is by simple command pip install Qiskit of machine learning. Okay, or you can also put in codes pip install within single codes Qiskit machine learning. Okay, also another optional thing is there, PyTorch and Sparse provides Qiskit machine learning inbuilt by using a simple pip command. Okay, we can do it in also in Google Colabs. Okay, so this is the command that initially you need to execute to install quantum machine learning in your. Okay, PyTorch is another very important upcoming technology. Even the statistics before 1 week, like TensorFlow, they're saying it is almost dead. Now PyTorch is the one, even Facebook and Google, they are planning to use it for their day-to-day regular things. Okay, right. So you have everything you are having here. Just if you click next and learn, hands-on you can learn. Okay, I will explain. See, you can see these are the popular quantum machine learning tutorials that you can see. So quantum neural networks, neural network classifier and regressor. You have quantum kernel machine learning. Okay, you have torch runtime, you have torch connector and hybrid QNNs. QNN is nothing but the same quantum neural network. Okay, you are studying till now neural networks using Python and TensorFlow. Okay, so normal machine learning you are studying. Okay, so now since quantum computing, quantum machine learning has become a reality, so we will be also studying QNN and QGAN. Okay, like how you study in deep learning GAN, here we'll be studying QGAN and quantum computing for loading random distributions. Also, we have Pegasus quantum support vector classifier we have, and quantum kernel training for machine learning applications. Okay, you also have for saving loading Qiskit machine learning models and string. The last one also we have effective dimension of Qiskit neural networks. Okay, right. So next we will see the basic level coding, okay, of quantum machine learning. So this is initially we start with quantum neural networks. Okay, so you can see here, these are the 4 important things we will be seeing: neural network, OP flow QNN, you have 2-layer QNN, you have circuit QNN. So neural network, you know very well, is the interface, okay, required for you for starting quantum neural networks. And a network based on evaluation of quantum mechanical observables is half-flow QNN, and 2-layer QNN is the one which we'll be using for implementation of convening. Okay, circuit QNN is a network based on samples resulting for measuring a quantum circuit. You can see here, even in quantum neural networks, we'll be using this NumPy. We'll import NumPy here, and then we have Qiskit import AER quantum circuit, and we import all the parameters required in circuit libraries with the help of the real amplitudes and ZZ feature map. Okay, we also import the required quantum mechanical observables like gradient, distop, polysam, okay, state FN, AR poly expectations. Okay, there are some utilities we'll be using for performing some algorithms and quantum instances. Okay, right. So to set the method to exactly calculate expected variables, we use this poly execution. Okay, so expected value is equal to, will be using this AER poly expectation, and the gradient method will be using here, and we'll be defining quantum instances like state vector and sample page. Okay, and we can see like initially we can go for 10 shots, the number of samples. As I told you, the scalability you can increase from 10 to 50, 50 to 100, 100 to 1000 plus. 1000 plus is for universal quantum computer. Okay, right. So a small introduction he has given it here. What is the neural network? Okay. What is that neural network and what is offloop QNN? You can see it is the parameterized operator from Qiskit and leverages Qiskit's gradient framework, which provides backward pass. Okay, it's an operator can instance be an expected value of quantum mechanical observable. Okay, right. So the offloop QNN also allows lists of operators and more complex structures to construct more complex QNNs. Okay, right. So you can see here how we are constructing a parameterized circuit. Okay, right. So the parameters is equal to parameter of input 1 comma parameter of weight 1. So as in normal conventional neural network, how you define a network, train a network with the help of input value, weights and bias value. Here also we will be doing using input 1 and weight 1. Okay, and the quantum circuit is called by passing one value. Okay, and the parameters values are passed with zeros and ones. Okay, then we will be constructing a cost operator using this particular syntax, and we'll be using a combine operator and circuit to objective function. Finally, we'll be printing OP1. Okay, so this will be the output that we'll be getting. Okay, after that, we have here random inputs and weights you can define, okay, using the random operator, okay, and the forward okay. So we have here, okay, the quantum neural network you can see here. This is a quantum neural network forward pass that you can see. Okay, using the input and weights, we'll be using this particular forward pass. Okay, so after giving random inputs, weights, and forward passing, we'll be going for batching the forward passing using QNN.forward of input 1 comma input 1 comma weights 1. Okay, so this array we are declaring here, and we can also go for backward pass using QNN1.backward command. Okay, and we'll be also using backward patching and array declaration, you can see. After that, we'll be combining multiple observables in a list operator command, which also allows to create more complex QNNs. Okay, so you can see after multiple observables you are using, again you are using forward pass and backward pass and array. The next important thing is two-layer QNN. Okay, so it is required for us to insert data, and second to train that particular network. Okay, right? So the default observable is you can see Z to the power of n, that is parity. Okay, so from Qiskit machine learning neural networks, you can see we import two-layer QNN. Okay, so if you want to specify the number of bits, number of qubits will be given 3, for example. There is Q0, Q1, Q2. I am giving here in the diagram. Okay, right. So how to specify the feature map for this? Fm is equal to ZZ feature map of num qubits, comma, repetitions is equal to 2. Okay, right. So next, specifying the amplitudes. How to specify the amplitudes that you can give here. Okay, and draw the diagram. Okay, right. And find next, specify the observables. Okay, and print the observable value, and then define the two-layer QNN. Okay, so we will be using the two-layer QNN command. We will be passing the qubits, feature map, and set value, and the observables. In the quantum instance, let it be QI underscore S1. After this, what you have to do? You have to again define inputs and weights. You have to go for forward passing and backward passing. These are important. At last, you will be giving array value. Okay. So next one is circuit QNN, fourth one. As we have discussed in the beginning of quantum neural networks, these four are important. So the fourth one is circuit QNN, which is based on parameterized quantum circuit. Okay. So this also uses weight parameters and samples for measurement. Okay. Right. So you can see here from Qiskit machine learning neural networks, we import circuit QNN. Then we have real amplitudes, okay, consisting of num qubits from entanglement equal to linear. Then one repetition I am taken, and we'll draw the output here. So you can see three values you have taken: Q0, Q1, Q2 qubits. 3 qubits you have taken, and repetitions will be only 1. Okay, and the output for sparse integer probabilities that you are considering. Okay, again we need to define how we specify circuit QNN. Okay, so here also we'll be passing the parameters and the sparse equal to true, and assign the quantum instance as QA underscore QASM. Okay, after that again you need to define the random inputs and weights. Next, quantum neural networks forwarding pass. Again, you need to go for forward pass and backward pass for the sparse matrix. And if any arrays are there, you need to define the array values also here. Okay, right. So the output in terms of dense parity probabilities. Okay, if you want to discuss, we will be discussing with the help of the specific circuit QNN. Okay, so here you can see the parity value initialized, okay, with the count 1, okay, and the output shape equal to 2, that is, it is required for a dense output. Okay, and the circuit QNN you have initialized here with parameters and parity, output shape, and quantum instance. After that, again, what you need to do, you need to define inputs and weights. Okay, also you need to go for forward passing, backward passing, and array declaration. Okay, and at last again we will be giving the output samples. Okay, so this is the array you can see. Okay, the parity samples will be different. So this, if you go for the version, so Qiskit Terra version we have used for 0.2, and Qiskit AER 0.10.4 version. Qiskit machine learning 0.4.0 is enough for starting initial machine learning in quantum computing. Okay, so you can see the Python version, Python compiler, and Python build. You can see which versions we are using. So the OS is mainly on Linux, and the 2 CPUs we can use, and the memory you can see here. Okay. All right. So right. So the next one important thing is neural network classifier and regressor. Okay, so when we started learning about quantum computing, quantum neural networks, okay, so we started learning machine learning. Initially, we discussed neural networks. So we have seen what is basics of quantum neural network. So when you go a little bit more deeper into that, we'll be seeing classifiers and regressors. Okay, so where we can use neural network classifier and neural network regressor. Okay, so we have in the tutorial, we have classification we can do using off-flow QNN and circuit QNN and the variational quantum classifier. We can do also regression. Regression with the off-flow QNN. Then we have variational quantum regressor we are having here. Okay, so we have some important basic level coding that I just wanted to show you here. So you can see we import NumPy and Matplotlib library, and from Qiskit we also import AER and quantum circuit. These are required mandatorily for performing machine learning in quantum computing, and we import the basic required operators. Okay, right, and optimizers and library files we have included all here. Okay, so see here we imported neural networks for two-layer QNN and circuit QNN. We also imported classifiers like neural network classifier and neural network regressor we have taken. Okay, so and then we can give an instance for this for 1024 shots. Okay, so classification can be done considering a classification data set you can take into consideration for executing the following algorithms. Okay, right. So these are number of inputs 2, number of samples are 20 as taken. So x is equal to 2 into just generated randomly for giving this particular diagram as output. He has taken random number generator. Okay, and the y values with this particular formula. Okay, so y1 hot is equal to np zeros of num samples comma 2. We use a for loop here in the range for plotting these particular dots. Okay, right. So either you will get a green color or you will be getting a blue color. Okay, how both of them are classified. Okay, that you can see the classification in the figure. Okay, right. So like this you can construct QNN you can do. Okay, so you can slowly one by one you can perform this hands-on session also. Objective function, how it varies with each iteration you can see here. Okay, similarly you can see little bit if wrongly classified what it will happen. For predicting that wrongly classified we are using this coding, and you can also go for a classification with a circuit QNN. Okay, so this you can see using these classifiers you can get this out, and they have also variation quantum classifier. You can see this one, and regression again you can prepare simple regression data set to execute the following algorithms. Okay, you can see here this is a simple output that you get it using random number generator. Also regression with off-flow QNN is possible. So you can see this will be the output regression. Okay, right. So also regression with VQR, variational quantum regressor is possible. This is a diagram. Okay, right. So like this you can practice. Okay, in IBM Qiskit. If you click next, we have quantum kernel machine learning also. So you can prepare this, you can study this at home when you find time. Please learn this supervised learning with quantum enhanced features. So using scikit-learn. Okay, we use Qiskit to calculate kernel matrix. Also, we use scikit-learn for kernel matrix for solving classification clustering algorithms. So you can see the classification code is given. Okay, and how it is classified. A dog data set is taken, how it is classified. Very neat diagram given. Output of that particular code. If you execute this code, you will get that one. Okay, Similarly, we can perform other kernel matrix training also. Okay, so I will share you this one in chat box, the link. I shared you for all panelists, please. Yeah, the link I have given for Qubits online learning. Okay, right. So after that, you can see the technology roadmap. If you can see, NASA is already using this quantum computing technology. Okay, so you can see this is an acknowledgement given by University of California, okay, Santa Barbara, NASA, okay, Ames Research Center, Oak Ridge National Laboratory. Okay, so these are the standard important links that are given, how they are utilizing AI Google block, quantum supremacy, how it is given. Okay, right. So these are some of the things which I would like to discuss with you all and share with you. There are a lot of things are there. You can see this is a Google AI blog. Okay, in 2019 itself they are given. Okay, posted by John Martinez. Okay, how now in USA NASA is utilizing quantum computing. Okay, so you can see, right? So various things are there. So Schrodinger-Feynman algorithm, many things are there. You can see this is real research that is expected at master graduate level. Okay, what is can be possible. Okay, right. Also, I showed you what is quantum machine learning. Okay. Also, now, like initially, students will be interested in learning from basics of quantum. Basics of quantum computing. So directly, instead of jumping into quantum machine learning, you can see Qubits. You just type it in Google. Okay, and just click this one. Okay, you can see here it starts from basic level. Okay, so you have release notes. You click this one. You have all the documentation that is available. Okay, to learn. Okay, what are the different versions are there? Okay, right. Till date, what are the versions are there? What are the new features are there? Everything explained. Okay, so you can also search for Qubits textbook. That will be very good, useful one for you. So learn quantum computation using Qubits. Okay, so you can see here on the left hand side, we start discussing from prerequisites, quantum states, qubits. Okay, what are the atoms of computation, representing qubit states, single qubit gates, case of quantum, again multiple qubits also, and entanglement is a very important one in research that we will be discussing. Multiple qubits, entangled states, phase kickback, okay, and classic quantum computation on a quantum computer. Also, quantum protocols. What are the different quantum protocols and quantum algorithms are there? We can study each algorithm. If you click any one important algorithm, like Shor's algorithm you want to see, just click Shor's algorithm. See, you are getting here on right hand side, Shor's algorithm introduction you are getting. Also, how to execute. Okay, Shor algorithm also code is given. You really will enjoy practicing all these. Understand the theoretical concept, also perform the algorithms. Everything clearly given with code. The solution explanation also is given. So I personally request you all to practice this and learn theoretical part of it also. So you can see complete explanation for Shor's algorithm is given step by step, every step. So this is the final output you can see. Similarly, you can see in addition to all the algorithms, you have quantum algorithms for applications also you have. Okay, so these things also you can perform, you can execute it. So implementations of recent quantum algorithms. So you can see the latest one, variational quantum linear solver also is given. Okay, and quantum edge detection also is given. Traveling salesman problem is given. Okay, also how to go a little bit more deeper into quantum hardware using quantum circuits also is given. This will really help you to really perform a BTech level project. Okay, and also you can publish a paper with the help of these results also. This will be very helpful for you. So I personally suggest you now to perform all this. Also quantum computing labs, there are some standard experiments you can see. Okay, so if you click again, see here, you have the algorithm and you have all the coding part also given. So first one, if you want to see, so quantum circuits, first experiment if you want to execute. So here you can see initial first program how we can do using gates with code and explanation, everything clearly given. This will really help you, okay, how to perform gates, not gate, okay, XOR gate, okay, so AND gate, everything. Okay. So I will share you this link also. This is a very good link for a beginner. Okay, right. This will help you really for starting quantum computing. Okay, right. So how to perform quantum computing on okay, IBM Qubits implementation. Okay, so these are a few things that I would like to share with you all. There are a lot of books also available online. Okay, right. We have very good useful information available. I will give you one link where you can download important textbooks for studying quantum computing. Just use this link z-lib.org. In search, you type quantum computing. You will get very good textbooks you can learn. So if you want some more like information, so you can also mail to me at drtbp 1981 at gmail.com. Okay, right? Yeah, I can help you out with latest research articles and latest books related to quantum computing. So that's all from my end. Brief introduction with quantum computing and quantum machine learning. So you would like to ask anything, you are free to ask. Okay. Yeah. Sir, Sandeep, sir.
Yeah, thank you. Thank you, Professor. Thank you very much for very detailed presentation.
It's my pleasure, sir.
Yeah, yeah, very good. Okay, so do we have any questions from attendees? Any attendee wish to ask a question? Yeah, we can see the questions in chat box. Okay, not questions are not there.
So I have given you some links in chat box.
Okay, right.
If possible, you can share it in Facebook also.
Sure.
Those two links are very useful for them for studying hands-on sessions.
Right. Thank you very much. We have no questions now. So on the behalf of LBF family and faculty, staff, honorable management, thank you very much, Professor Kolla, Bhanu, Prakash, for joining us.
Total, how many participants were there, sir?
Students are being on web live on Facebook, sir.
So we cannot have a number.
Yeah, also students are there in classrooms. They are watching from screens.
Okay.
Yeah. Thank you very much for joining. Thank you very much, and it was really pleasure to host.
Thank you, sir. Thank you.
Yeah, we shall invite you for more lectures in coming time. Thank you very much.
Thank you, sir.
Audience, also please, thank you, convey our regards to everyone. Thank you. Take care, everyone.